to go live on YouTube now. And you can take the screen if you'd like.
Sure.
All right, welcome everyone to today's seminar. Today we'll be continuing on from our last seminar on a discussion of the Center for Geospace Storms. And we have two talks today from Anthony Sciola and Dong Lin. Our first talk will be by Dr. Anthony Sciola. He got his bachelor's degree in physics from Old Dominion University in 2015 and his master's and PhD from Rice University in 2018 and 2021. His PhD thesis involved numerical modeling of the magnetospheres of rocky exoplanets, and is currently a postdoc at JHU APL, where he's part of the CGS team and focusing on inner magnetospheric dynamics and coupling the system as a whole. With that, Anthony, if you would like to start.
All right, thanks very much for the introduction and for having us today. So I'll be telling you about our recent work on modeling the buildup of the storm time ring current via mesoscale plasma sheet flows.
Sorry, Anthony, I don't mean to interrupt. You're in presentation view or presenter view right now.
Okay, it was right the first time. All right, is that good?
Yeah.
All right, solid. Thanks. Okay, so everyone knows that a major component of storms, now the zoom window is stuck on my other screen, okay, is the buildup of the storm time ring current. But it's still sort of up for debate exactly how that plasma and the energy gets transported from the tail side reconnection region all the way to the ring current. And so it was initially thought that that was done through global scale convection. You have this global scale electric field that convects everything inwards. Intermediate models have shown that global scale driving can explain transport from around near geo down to the ring current. But there's some other models that have suggested that this global scale field is not sufficient in transporting enough energy all the way from the tail. And so on the other hand, bursty bulk flows, or BBFs, have been observed for a long time. They are azimuthally localized flows that transport dipolarizing magnetic flux and enhancements of hot plasma earthward. Yang 2016 showed that as opposed to driving through the global scale field, driving via entry depleted bubbles, which is sort of the theoretical description for BBFs, builds up a much stronger ring current. It can explain the type of ring current we see during storm time. A major factor of these bubbles is that their penetration depth is determined by the bubble's fluxtube entropy relative to the background. And this makes them capable of penetrating all the way down to geo if their entropy is low enough. And here's just a simple schematic of that on the right, where blue is the background fluxtube entropy, and then a bubble with depleted entropy will propagate in until it reaches equilibrium. And so BBFs are believed to be the sole contributor to global scale depolarizations of the magnetosphere during substorm expansion. And so along with many other reasons, the question arises of how much of these actually contributing to the buildup of the ring current versus global scale convection. It was a very challenging question to answer with observations quantitatively. There's very, very few studies with it. Giolito 2014 used Van Allen probe observations of injections that reach below geo to estimate that BBFs contribute about 30% of the total thermal energy to the ring current, but this required lots of assumptions and extrapolations. Now, of course, it's much easier to quantify things with a numerical model, but they come with their own caveats as well. Yang 2015 used standalone RCME to estimate that BBFs contribute up to 60% of the total energy density to within geo, but this has the caveat that they have to use parameterized bubbles along their static outer boundary at 15 instead of using a more self-consistent coupling with the global scale and self-consistently produced bubbles. Kramer got closer to realizing that by using OpenGGCM MHC model coupled with RCM, and found that BBFs are responsible for 65 to 85% of the total inward plasma transport to below geo, which is a really nice study, but this unfortunately is only looking at the mass transport and not the energy component of that. and is also looking at the inward transport and not the net contribution. And we'll see why I want to make that distinction a little bit later. And then also, I didn't give much background on this, but it's also unclear exactly how bubbles are related to the observed evolution of the ring current energy spectra throughout the storm. And so those are the two main sort of questions we want to look into today, is both the buildup of the ring current and its evolution in energy spectra over time. We'll be doing that via a case study by simulating the March 17, 2013 storm. For that, we'll be using the Multiscale Atmosphere-Geospace environment, or MAGE model, which you heard a lot about from Slava last week. And we're not using all the models here on the right, just the Gamera MHT model, Remix for the ionosphere, and then RCM for the intermagnetosphere. And so we're doing this both to understand those questions that we just talked about, but also from the perspective of a highly coupled geospace model. It's incredibly important to get this ring current correct, because we need to be able to self-consistently reproduce its radiolocation, its azimuthal extent, its intensity across all energies, because of how these couple to the rest of the system, both on a large scale and through energy-dependent processes, such as precipitation and charge exchange and all that. And so once we have this ring current sort of being populated correctly, we can couple it with all these other processes as well. So we will get right into the simulation. Here's a quick overview. On the top here, I have a DST plot showing the observed and modeled DST in blue and orange. But most importantly, I'm also showing the DPS DST evaluated within, for all closed field lines within 6RE of Earth. This is useful because it's directly proportional to the kinetic energy within that region. And so this shows very nicely that we're getting our buildup of the energy population within 6RE between 8:30 and around 10, 11 o'clock here. Then below that, I'm just picking some select times from here to show that, the ring current's obviously building up over this time. We'll quantify that a little more later. But also, during this period, we have many mesoscale flows. They're very azimuthally localized. This is showing the radial velocity in this middle panel, sorry. And then below that, we have delta BZ, which is the BZ component with the dipole subtracted out. You can see that these flows are carrying dipolarizing flux with them as well. So just a quick note on their spatial scale and their origin is here. What we're looking at is we have the Earth for reference, and then I'm taking a bunch of spherical slices through the tail, where we have the dusk side over on the right here, and then extending to past midnight on the left here. And there's a lot going on here, but the main point to show is that you can see these flows emerging from the tail and coming through many, many RE to penetrate all the way down, in some cases to below 6 RE here. Not all of them make it, but of course, very many do. And another important factor about this is that we see return flows on either side of those, and they actually end up transporting outwards a non-trivial amount of plasma energy. And that'll be important very soon as well. And so one last slide to convince you that these are truly bubbles, or sort of BBFs in nature, is I'm taking a slice through this night side arc with a radius of 6 RE and showing several quantities as a function of MLT and UT on the y-axis. On the top, we're showing the enthalpy flux, which is, in other words, a measure for the thermal energy transport through the surface. We can see, again, we have these very localized flows. They only last for a couple minutes at a time, and very many of them have return flows accompanying them, like these guys over here. You can see they are also carrying dipolarizing flux, and that their entropy is lower than the background. So these are truly, bubbles by definition. I'll use the term bubbles to not get too confused with the stricter terminology of BBFs, but it's understood that, some of these would qualify as BBFs, but we'll just generally refer to them as bubbles here. Okay, and so with that, we'll go on to quantifying their contribution to the ring current. I'm going to take this top plot here and then show it again, but with these boxes overlaid on it. What we did was we have a pretty simple method of just picking out where these BBFs are through the surface, these bubbles through the surface, but then also extending that range that we're calling due to BBFs by an azimuthal extent of plus or minus 1 RE so that we capture the effect of those return flows, because without the BBFs, those return flows would, of course, not be there. And it's really important because those return flows can transport outward about 40% as much thermal energy as the inward flows are bringing in. So it's important to include that factor. But then what we can do is we can just very easily sum up for every point in time the net amount of inward transport of the enthalpy flux or of the thermal energy contained within bubbles and outside of bubbles. And we find that the bubbles are responsible for 50% of the net inward transport for this simulation. And this is technically a lower bound, depending on what question you're asking. If your question is how much do bubbles as a whole generate, or how much they contribute from transport from the tail all the way into the ring current, can be a little bit trickier because you can have bubbles that don't penetrate all the way in, but they're still transporting, the plasma most of the way there. Then they get to the equilibrium point, they blend in with the background, and you have this convective flow that can bring them in the rest of the way. We're not accounting for those bubbles in this situation, only the bubbles that actually make it all the way down to 6. And so you can kind of consider this as a lower bound on the contribution of BBFs. And then this is probably something that everyone already expects, is here we're showing the value in blue and time derivative in orange of the total kinetic energy contained within the 6RE domain. And this is just showing that the greatest instances of enhancement in the total kinetic energy corresponds very well with these injections. So they are the primary contributors to the accumulation of energy below this boundary. Okay, so now we're going to move on to looking at the evolution of the energy spectra. And we'll start that by looking at a data model comparison between RBSP-B and RCM along the virtual spacecraft trajectory. On the left here, I'm showing the energy spectra of proton intensities between 10 and 200 keV. On the top is from the instrument RBSpice. On the bottom is RCM along the same track. We can see that they're agreeing quite well, especially in this middle orbit here. And if I can play this movie back a bit and stop it close to here, we can see that the spacecraft is flying through the inner edge of the ring current right at the start of orbit 2. And so because of the timing of this and similarity in magnitudes, we can sort of conclude that we're accurately capturing the ring current magnitude and location at the inner edge pretty well. And then on the right, we're showing it a little more quantitatively. It's just the same information, but taking slices out at specific energies. And again, in this middle orbit, they agree quite well. This is across the energy range that's most responsible for the ring current pressure. This is especially true for the 50 keV band. And we can see that, there are some exceptions, like at these high energies, there's this dropout here. That corresponds to the sort of missing background population in here. And so I'm happy to speculate maybe afterwards why we're missing that, but don't want to go into it too much here. And then also it seems like we are seeing a more intense ring current, but also on the downward edge on the end of this orbit here. So as we fly through this region, so our ring current is more intense and a little bit further out than what's observed in reality. And this can be because there's lots of sort of competing processes happening on the dawn side here, where you have eastward E cross B drifts competing with your westward gradient curvature drifts. And so it's a very complicated region to get correctly. And so it's actually a really nice way to sort of get a feel for how well we're doing on those different metrics. And okay, so now we'll actually look at the evolution of the energy spectra. So on these equatorial plots, I have these 3 dots. We're going to look specifically at this innermost one. This is located at 3.8 RE with an MLT of 21. And I'm plotting the cumulative pressure as a function of energy and time. And the color contour is the cumulative pressure, and the white lines are the median and quartile values of that pressure. So basically, this middle line at 50% means that at this point in time, 50% of our total pressure is coming from protons 20 keV and below. And so to dig into this time series a bit, we can see that the plasma reaches 3.8 RE around 9 UT here. And then we have the starter ring current early on, which has a median energy around 50-60 or so, but it's very clear that this isn't contributing very much, and that when the flows from the tail actually arrive, they're creating a whole lot of this pressure, and the median energy in this case is at 20 keV here. And then over time, this increases pretty quickly to about 30 or 40 keV, and then gradually over the next several hours, it increases to 70 or so. So this is interesting in itself. This can be directly compared to some analysis done with observations. But of course, the next question is, what's the cause of this evolution over time? It can be due to your source in the tail becoming hotter over time. You're transporting in the hotter population. It can be from just localized adiabatic heating. If for some reason you have depolarizations in that region, you get a strong magnetic field, you're going to heat your plasma as well. So it could just be that it's the same population just getting heated locally, or it could be because you have losses that are affecting energies in different rates. So we will look into that now. I'm going to take this plot here and show it again in the middle. And then on top, we're first looking at the sources. This is just looking at the net energy flux through that 6RE arc that we looked at earlier, but just for a longer period of time. We see that initial period of buildup here that we've looked at a little more detail earlier. That explains where this population is coming from here. And then it can also explain this hotter population within this region. You still see some activity. Then it's relatively quiet for a while, except for some couple features throughout here, where you see an increase in the pressure here, but not so much of an effect on the energy. But then here we get another brief period where you get a little enhancement in the pressure and a bit of an increase in the median energy there. And so the injections over time are contributing to this, but are not really the sole drivers of this evolution in this case. We can then look at a factor of the flux tube volume. This is directly proportional to the energization that the plasma would experience due to changes in the flux tube volume. We can see it's quite variable over this time period. It goes between 26 and 28. So it's really only changing by less than 10% of throughout at this period, and it goes back and forth. So this doesn't really seem to be a good explanation for this sort of more constant energization over time. Not energization, but shift in the median energy. And then finally, I am showing the intensity as the proton intensity as a function of energy and time, and then taking two specific energies out of that, shown by these lines here, 10 and 50 keV, and plotting them down here as their own time series. And the y-axis is a log scale. And so, of course, they both intensify around 9 UT, but we can see that aside from this activity towards the beginning, 50 keV protons stay relatively constant throughout this period, whereas 10 keV protons are decaying pretty steadily throughout this whole period. And so this is coming from a combination of charge exchange affecting your lower protons at a faster rate, and also the fact that these guys are on open drift orbits, whereas the 50 keV ones are not. So these aren't trapped in the system so well. So altogether, this shows that the explanation, at least in this case, for this evolution over time is a combination of both the evolving source population in the tail and the transport of that source population inward, and the energy-dependent loss processes. And so this is just analysis of the specific storm, but this will be really important for us in the future because this gives us essentially a larger sort of surface area to validate our model over, because getting the ring current right really entails getting our sources and sinks, and of course the propagation once it's there correctly, but very much the source and exactly what the energy spectra is that whatever the transport mechanism is bringing inwards. And so we can compare this to Themis data and all that. We can look into similarly the evolution of the electron energy spectra over time, which is going to be even more impacted by things like precipitation, and we can compare that to, for example, DMSP and all that, which we might hear about pretty soon. But yeah, so that will be a sort of avenue for future work. And so in conclusion, we've shown that there's further support from the MAGE model, from the modeling side, that bubbles/PBFs are responsible for contributing a significant amount of plasma pressure to the storm time ring current. Of course, it'd be really great if we can sort of get to this question better with observations in the future, maybe with an imager might give us the actual capability to see these flowing into the tail instead of only having multi-point measurements where it's much harder to differentiate or to know if you're actually viewing the same bubble at different distances. Imager would really help solve that problem. We've also showed that the model is accurately reproducing the observed storm time intermediospheric characteristics, including the injection profile, which I forgot to touch on, and the comparison to RB-SPICE, the spectra. We're also getting the ring current location and intensity right pretty well as the energy spectra over time. And like I mentioned at the beginning, this is critical for being able to confidently model particle precipitation, charge exchange processes, and storm time recovery from first principles. And I already touched on this last point about where our evolution was coming from, and so I will leave it at that. So thank you very much.
Excellent. Thank you, Anthony, for a wonderful talk. We have a couple questions. One is from Krishna, and I believe it's related to slide 11. Could you elaborate on how the DST is related to the energy flux?
How the DST is related to the energy flux. Maybe that's in reference to the DPS DST. Yeah, so it's a method of estimating it's basically a relationship between the total kinetic energy within the region you're looking at and the effect that that population has on DST. Now, there's been lots of papers showing that these aren't really correlated. You can't really use these as a proxy to get from the real DST to the energy population, but that's really not what we're doing here. I'm not necessarily trying to say this much DST is coming directly from the ring current. I'm just using it as a way to show on the same sort of units as on this plot that there's still a direct relationship between the total kinetic energy within that region and this quantity expressed in nanotesla, essentially. And so since this is, constant throughout here, then there isn't much change in that kinetic energy, and then it's decreasing throughout here, and that's when you're getting your influx of thermal energy to below 6 area, and that was sort of the reason for using that metric.
All right, thank you. So she does have a follow-up. Does the total energy flux you have represent the Poynting flux, the kinetic energy, and the enthalpy?
So, I do have a different version of this plot where I show the contribution from enthalpy, Poynting flux, and kinetic energy, and that actually does show up, although not in very good quality on here. That's what this is. We can see from here that the majority of this, by the time you get to 6 RE, it's in the form of enthalpy flux. So it's already thermal energy, basically, by the time it gets to 3. And you can have some conversion from magnetic to thermal lower than that as it moves in, but it's already mostly in thermal energy. And so in this comparison here, this is all looking at the net enthalpy flux here. This is looking at the total kinetic energy below that region. So there's still like a slight room for, of course, losses on the top here coming out of the day side and also conversion, but these should still track pretty closely with each other since everything's already in the form of thermal energy by the time it gets to 6. Not everything, but very much so.
Excellent. Right, and I have one final question. You did mention precipitation as one of your losses or potential losses. Are you guys able to investigate wave-particle interactions at all?
We are working on that. I'm not going to say too much about it because I think that might be in Dongstop coming up. But yes, that's something that we are working on, and I think we'll hear about in just a minute.
Excellent. Awesome. Thank you, Anthony. And with that, we will move on to our next speaker, Dong Lin.
Hi, can you see my slides and hear me well?
Yeah, we have a full screen presenter view.
Okay, that's great.
All right.
Okay.
Yeah, so I'll do your intro quick, Dong. So Dr. Dong Lin got his bachelor's degree in space physics from the University of Science and Technology of China in 2011, and his master's degree in space physics from the University of Chinese Academy of Sciences in 2014. He got a PhD in electrical engineering from Virginia Tech in 2019, and is now an ASP postdoc at NCAR HAO. He was promoted to apologies. He is now a project scientist and was recently promoted in January 2022. Dr. Lin is a member of the CGS modeling team, and he has been primarily working on characterizing auroral precipitation and magnetosphere-ionosphere thermosphere coupling. With that, Dong, if you would like to start.
Okay, thank you, Kyle. Good morning or good afternoon, everyone. Yeah, this is Dong Lin from NCAR HAO. It's a great pleasure to present at the NASA Magnetosphere seminar and share our recent work from CGS on auroral precipitation and conductance. I'd like to first acknowledge my collaborators from a number of institutions as listed here, particularly the CGS modeling team, and with whom I have been working with most closely. As space scientists, I believe many of you have been using Aurora to illustrate what our research is about. So indeed, Aurora probably the most well-known space science phenomenon that even the general public can observe and record with their camera, not relying on any scientific instrument. And Aurora were probably also among the oldest observations that has inspired modern discoveries in the magnetosphere and the entire geospace system. So as space scientists, we can make use of more advanced cameras. Basically, I mean images here that are on board either a satellite or on the ground. So from this image data, you can see that auroral activity is actually very dynamic and featured by different structures, and also spans a broader range of spatial and temporal scales. As space physics, we want to learn more about just the optical signatures. So we have learned that auroral precipitation are basically charged particles, electrons and ions from the magnetosphere that deposit their energy in the atmosphere. So it's critically important to know the distribution of those precipitating particles, or what do we call the energy spectrum. So using the particle detectors on board the DMSP satellites, researchers in the past have identified different physical mechanisms that contribute to the precipitation. For example, in this top panel here, you see these red bells. Basically means a number of electrons got about the same amount of energy. So this is a signature that all these electrons have been accelerated by the same potential drop. So that's how they got the name monoenergetic. On the other hand, in the bottom plot, you can see a different type of acceleration which occurs over a broader range of energy levels. So this is attributed to the RFN waves that accelerate a broader range, and they got the name of broadband electrons precipitation. And in the categorization by Newell et al. 2009, they termed all the rest of electron precipitation, which appear as very diffusive here, as diffuse electron precipitation. So this is like a three typical example of electron precipitation. And by statistically putting the different types of precipitation together, we can learn more about the differences in the underlying physics. For example, this is like a statistical map of the monoenergetic electron precipitation. And you can see most of the electron precipitation resides on the upward phenon current in the dusk side. So again, this has to do with the acceleration in the upward current. While the diffuse electron precipitation is more preferred towards the dawn side. And this has to do with eastward drift of the electrons in the magnetospheric source region. The broadband electron precipitation is mostly in the pre-midnight or the near the dusk side Casper region, and that has to do with the efficiency of the orphan waves. And also, statistically, we can, well, the previous researchers have evaluated like the relative contribution of the different precipitation to the total precipitation power as well as the number flux. And as you can see from the table, these three types, mono, diffuse, and broadband, contributes the most to the total power and the number flux. So that's why we focus on these three primary types of electron precipitation in the current study. So in addition to the energy brought by those precipitating electrons, they are also playing critical roles in the coupled magnetosphere, ionosphere, and the thermosphere. So the precipitating electrons are important carriers of the upward Phelan current, but most importantly, the precipitation generates ionospheric ionization and conductivity in the high latitude ionosphere, which then regulates the high latitude electrodynamics, including the Joule heating and the convection pattern, as well as the current closure path. So this is particularly important because they can also map back to the magnetosphere so that regulate the counterpart in the magnetosphere. So here's a summary of our motivation and the goal. We know auroral precipitation plays a critical role in the loss of magnetospheric electron ions. They can also generate ionospheric conductivity, which then regulates the electrodynamic coupling and energy dissipation. So we hope to develop a physics-based characterization of precipitation and conductance in order to fully understand the geospace system. So our primary tool here at the CGS is using the MAGE model, multiscale Atmosphere-Geospace environment. Anthony just showed a grand blueprint of this MAGE model. What I'm showing here is the current iteration. You can call it the MAGE 1.0. Here's like the critical components of MAGE 1.0. It includes the Gamera global MHD model for the magnetosphere. And when it gets close to the Earth, we know ideal MHD is no longer a good assumption. So we use the Rice convection model to deal with the ring current and the convection drift of electron ions in this inner magnetosphere region. And in the bottom, we use the TI-DCM model to deal with the plasma and the neutral dynamics as well as chemistry in the ionosphere thermosphere. And all these model components are two-way coupled through this remix module, which is responsible for the exchange of like Phelan current, precipitation, conductance, and the convection pattern, which is also the potential solver here. Regarding precipitation, we are making use of different components that are based on different physics assumptions to deal with the different types of precipitation we just talked about, and I will elaborate later. So for the monoenergetic, we are basically taking the Friedman-Lamel relation, which has been used by many other global models as well. Basically, this relation was inspired by an earlier of the rocket of, oh, sorry, I somehow triggered my theory. Yeah, this Friedman-Lamel relation was initially inspired by the rocket measurements of monoenergetic precipitation, where they found a linear relation between the energy flux and the potential drop square. So it started from adiabatic assumption and assumed that the upward Phelan current is uniquely carried by the precipitating electron, and derive the flux relation between the source region and when it reaches the mirror point. So this relation is what we implement in MAGE model for monoenergetic, and is relying on the large-scale MHD quantities of phyton current as well as thermal flux. So the diffuse electron precipitation is, on the other hand, attributed to the wave-particle interactions in the magnetosphere. There have been many studies on like a various type of waves and their interaction with the electron ions in the magnetosphere. For example, the Gauss wave, Higgs wave, time domain structure, for example. And each different wave has their own characteristic distribution, like the occurrence, location, energy preference, and their dependence on the geomagnetic activity level. Since this wave-particle interaction involves particle dynamics or physics, that's not directly solvable by the Gamma MHD model. So instead, we make use of the RCM ring current model to deal with the convection drift and the variation of those particles. A few years ago, Margaret Chen and her collaborators who have been using the RCME model came up with the idea of dealing with the contribution from different waves separately. So they started by assuming that inside the plasma pores is mainly contributed by Higgs waves, and the outside is mainly by Gauss wave. And then they take advantage of statistical distribution of the electron lifetime so that they can derive how much electron can be precipitated due to these different waves. So at CGS, we have implemented a similar approach, but we have upgraded the Gauss and Higgs wave models that have better data support. So this is like based on a modern wave model that we are using in MAGE. Last piece is about the broadband electron precipitation. So physically, we know the so-called BBE. Well, first of all, they are relatively soft compared to the monodiffuse we just talked about, but they are also important in the coupled MIT system, such as impacts on the atmospheric density anomaly in the Casper region. But physically, BBE is mostly driven by the kinetic arcing waves. So that's, again, not directly solved by MHD models. However, statistically, people have found a good correlation between the BBE flux and the phyton Arfanic Pauling flux. The later, the Pauling flux, Arfanic Pauling flux, something that we can directly solve in our MAGE magnetosphere model. So in this precipitation derivation, we simply use the Arfanic Pauling flux to parameterize the BBE precipitation. So here is a snapshot of the three types of precipitation we just covered. So let's just start from the middle panel in the bottom. This is the energy flux of monodiffuse electron precipitation. And first, you can see there is a arc-like auroral structure on the dusk side. And if you compare this with the phyton current plot on the bottom left, you can see it's mostly inside the dark blue area, which is the upward phyton current. This is just where the Friedman-Lamé relation is triggered. You also see another belt starting from pre-midnight to the noon sector. This is like a diffuse electron aurora. And from the model, we know it's coming from the inner magnetosphere where the Gauss wave model was triggered. And we have these black curves as a marker to indicate the location. This is basically where the 60-degree magnetic latitude is mapped to the equatorial plane. And further, you see some auroral structures. And if we do the phyton mapping from the ionosphere to the magnetosphere, this is just like a projection in the equatorial plane. And you can then compare this plot to the residual BZ in the equatorial plane. You can see this kind of auroral structures are basically contributed by the flow channels that approach the Earth. And then lastly, you see another distribution. This is the broadband precipitation that we just derived. And again, it's just based on the field line Arfanic Poynting flux distribution. Currently, we just assume the monodiffuse are exclusive spatially, although we don't have to do that, just as a starting point. And again, the BBE is regarded as a soft component on top of that. So we also try to validate our precipitation model. So what we use is a long run for 27 days. So this is one solar rotation cycle. And we choose this 2013 interval from May the 23rd to June the 2019th. This period was chosen because it contains an intense storm and some moderate storm. So it's a good representation of different storm conditions. And you can also see the statistical distribution of the clock angle and the solar wind speed categorized by different clock angle beams. Let me just quickly show a few data model comparison. So first reference point is the DMSP measurements of the total energy flux, as well as the cross-track horizontal ion drift. So here is like a one orbit on June the 1st, when the DMSP F-17 was crossing the southern hemisphere from the dusk side to the dawn side. So it flies this way. And you can see it first encounters some mono auroral structure, and then later it gets into a stronger diffuse auroral oval. And this is a comparison of the convection pattern, which you can see it's also in a very good agreement. This is like the convection pattern, the field line current from the model, and the bottom is just a proxy of the field line current from the DMSP measurements, but basically shows a magnetic variation where the gradient implies the field line current. So overall, this is showing a good data model comparison. And that's just a one snapshot. We don't want to only show good results. So this is like a summary of all the orbits from 3 DMSP satellites during this one day. And you can see overall it's reasonably close to each other, although some small scale structures from DMSP data is not captured in the model. But this is kind of understandable because currently we only consider the monodiffuse and the broadband precipitation. However, in the DMSP measurements, it actually contains everything. Here's another effort trying to evaluate our model performance. So we also compared the hemisphere power from the MIDGE model with those from the Ovation Prime empirical model. And this is just the time series of the total power, and also when they are decomposed into the 3 components. So Ovarian Prime does provide separate contribution by this monodiffuse and broadband. So overall, it's also qualitatively consistent. During this period, on June the 1st, the MIDGE power in diffuse and broadband is stronger than the Ovation Prime. This has to do with the stronger driving condition during this period. Remember, there was an intense storm. So Ovation Prime, as we know, is not this is not the most recent version. There is a more advanced Ovation Prime 2013 that may give a better result for storm time, but we're also trying to further evaluate the performance during this strong storm period by referring to other data sources. But overall, you can see the power results are pretty reasonable. Lastly, one of the most important effect of precipitation is a contribution to ionospheric conductance. So in the community, as well as in our model itself, the Robinson formula has been the classic relation, empirical relation have been using. Basically, it's assuming the Peterson and Hall integrated conductance is a function of the mean energy and the energy flux of the precipitation electrons. It's also assumed it's Maxwellian distribution. And other than precipitation, we know the solar EUV radiance can also generate conductance on the day side. And this one is simply described as a function of the F10.7 and the solar zenith angle. These are just the empirical relations we use when we don't have a first principle IT model. But image, since we are two-way coupled with TIDCM, which deals with the entire ionosphere thermosphere, so we can actually derive the conductivity from first principles with the formula listed here. As you can see, it's a function of electron density and also the gyro frequency, collision frequency with the neutral components. But so far, we are still assuming the precipitation is Maxwellian distribution. Here is like a one cut at a certain local time where you see the electron density distribution over altitude and latitude. And this spot is simply because there is precipitation electrons over there, so that they generate more ionization and electron production there. And you can also see a peak in the integrated conductance. This is just a demonstration how TIDCM deals with conductance and conductivity. But like I just mentioned, the current method is based on Maxwellian assumption. However, that's just an assumption, and we know the shape of the precipitation spectrum actually matters. This study by Fang et al. 2010 already showed that how a arbitrary spectrum can deviate from the Maxwellian result. So in the next, we are going to implement this Fang approach. Basically, it's no longer constrained by the Maxwellian assumption, and we can deal with arbitrary. And on the other hand, since we are making use of the RCM model to deal with the precipitation at different energy levels, so we can indeed derive a full spectrum for the electron precipitation rather than relying on any specific assumption. This is just like an example of the precipitation spectrum derived from RCM and compare with DMSB. Other than the spectrum, another important factor in determining the conductivity profile is the thermosphere neutral density. So the Robinson formula we just talked about was actually based on the MC's empirical model. And in a recent study by Stephen Kepler et al., they actually suggested a modification to that Hall-Peterson ratio. And that difference is partly attributed to the different neutral density models they used. So this just to tell you the neutral density profile matters in getting the correct conductivity. And most importantly, when we talk about the geomagnetic storms, the actual neutral density profile can be allowed to deviate from what the empirical model like MC suggests. So this is our recent work on the SpaceX storm, where you can see the MC's profile of neutral density is very different from what the swarm data and what the major model suggests. So this is another important factor to be considered. With all those derivation of precipitation, we can actually do more studies in MI coupling and the storm time geospace. Here I'm just showing one snapshot from our recent work on the so-called sub-auroral polarization streams, or SAPs. And we especially using the drift phase-based diffuse precipitation, we can now more reliably resolve the SAPs on the dusk side. And in a recent work, we were able to explain the formation of the SAPs on the dawn side. And you can check out more details in these two recent papers. So this also highlights the importance to get a proper description of the electron precipitation in order to understand mesoscale structures, particularly such as the SAPs we are talking about here. So here is my conclusion page. So basically, we derived the three primary types of electron precipitation: mono, diffuse, and broadband in our MAGE 1.0 model. And they are characterized based on the different driving mechanisms, including both MHD and drift physics. And we have also compared with the DMSP and the Ovation Prime data products. And I also want to highlight, emphasize the ionospheric conductance is impacted by both the spectrum and the neutral density profile. And that should be taken into account with a first principle IT model. And so far, the precipitation and the conductance model has facilitated geospace storm studies, such as SAPs. And lastly, as some of you know, I'm a co-chair for this GM focus group on menispheric precipitation and their effects in the MIT coupling. So we welcome you to join our focus group in San Diego this June in GM. Let me just stop here and take questions. Thank you very much.
Thank you, Dong, for a wonderful talk. We do have a question from Krishna regarding slide 15. In slide 15, the field line current has the opposite trend to the energy flux after the vertical line there. Is there a specific reason for that?
You mean field line current has the opposite trend?
Yeah, Krishna, do you want to elaborate?
Yeah, hi, can you hear me?
Yes, yes, please.
Yeah, if we see the trend in energy flux and field aligned current, you just go to the next, like around the next peak, second peak.
This one?
Yeah, if we
Okay.
see when there is a peak in the energy flux, the field in the field aligned current, there is a dip, like it is a crest in. If you see the trend in energy flux and the field aligned current after this vertical line, they are both opposite to each other. Is there any particular reason behind that?
You mean why this
Yeah,
precipitation peak is
whenever there
residing
is a, yeah,
in this
whenever
field line
there
current?
is, yeah,
Yeah, so yeah, thanks for the question. So this peak is actually, if you look at the map of energy flux here, it's actually near the dawn side. You can see MLT around 8. So it's really when it was crossing this part, and this part is actually in the diffuse precipitation. And for the diffuse precipitation, is determined by the wave activity in the magnetosphere, although we are using that empirical lifetime distribution. But it's not directly determined by whatever field line current here, although if you look at this field line current sampling, it crosses the upward. Well, this positive is should be downward actually, because this on this plot the purple is downward and the yellow is upward. So actually, I think that the field line current sign here is a little bit different. But just from this 2D map, you can see this dip corresponds to the yellow part. So that's again upward. But again, for the diffuse precipitation, it's not directly determined by the field line current in this case, because it's determined by the wave distribution.
okay, thank you very much. Thank you.
Sure, thanks.
Great. And I have one follow-up. When you show the discrete auroral arc on a couple of slides before this, do you see that discrete auroral arc during quiet times too? Like when the tail isn't as dynamic as this?
I would say sometimes, because when I say arc, it's actually more morphological description. But let's just get back to the original definition of mono diffuse or broadband. So this is usually in the upward Phelan currents and when the Friedman-Lamel relation is applicable. So in that case, when you have a strong enough upward Phelan current, and when the source region has a not so strong thermoflux, you would expect a potential drop needed. So that's when you can expect a monoenergetic auroral arc to be there. So we do sometimes see those during relatively quiet time. So again, it's determined by the relationship between the Phelan current and the thermoflux.
Okay, excellent. Thank you.
Yeah.
So that's all the questions we have today. I'd like to thank Dong and Anthony again for wonderful talks. Our next speaker is going to be Larry Kepko, and he will be speaking on Monday, February 27th, and we will have no seminar next Monday due to the holiday. I hope everyone has a wonderful week, and I look forward to seeing you in a couple of weeks. Thanks again, Dong and Anthony.
Thank you. Thank you, everyone.